Welcome to this explainer. If you've ever looked at a crazy diagram full of intersecting lines and triangles and felt like you were staring at a locked safe, well, you're absolutely in the right place. Today, we're going to equip you with the mathematical tools to solve these complex geometric puzzles, literally step by step. It's like we're becoming geometric detectives today. So here's the big question we're tackling. How do we actually unlock the hidden measurements inside any triangle, using just a few basic clues and a really sharp detective's eye? We're going to dive into the secret relationships between lines, points, and angles. And the coolest part? This lets us find missing pieces of information without needing to physically measure a single thing ourselves.
Okay, here's our roadmap for today. First, we'll look at parallel lines and transversals. Then, adding some algebra to geometry. Third, rays and triangle midpoints. Fourth, the triangle midsegment theorem. And finally, we'll put it all together by solving some complex triangle puzzles. Let's jump in.
Section 1. Parallel lines and transversals. Okay, so looking at Theorem 3.1, this introduces a seriously brilliant rule of proportion. It basically says that if a straight line, which we call a transversal, cuts across several parallel lines, and the parts of that transversal trapped between those lines are exactly equal in length, well, something kind of magical happens. It means the segments of literally any other transversal crossing those exact same parallel lines are going to be equal to each other too. So if segment AB equals BC and that equals CD on the left, then over on the right, EF has to equal FG, which has to equal GH. It's just this perfect ripple effect of equality.
Let's actually see this in practice with example 1. We've got parallel lines crossed by two transversals, right? Notice how on the left side, the line AC is broken into three perfectly equal pieces, AY, YX, and XC. Now, because those segments are equal, our theorem absolutely guarantees the segments on the right side transversal, that's AB, are also perfectly equal. So if we look at that right side, the total 15-centimeter length of AB just gets split evenly into three pieces. That means AD, DH, and HB are each exactly 5 centimeters. And if we just want the length of the bottom two sections, segment BD, we just add 5 and 5, so boom, segment BD is exactly 10 centimeters. Easy, right?
Moving right along to Section 2, adding algebra to geometry.
Now this is where it gets really interesting. Let's combine this new geometric tool with some algebra to solve a slightly trickier puzzle. Looking at example 2, we have the exact same setup. Parallel lines, transversals. We know the segments on the left transversal are equal, so naturally, the ones on the right are equal too. But here's the twist. The transversal segments on the right aren't just simple numbers anymore. Instead, they're algebraic expressions, 2x plus 1 and x plus 5.
Let's take a quick second to breathe here, because this is how we build the bridge between shapes and formulas. Our geometric truth on the left, the fact that segment AH must perfectly equal segment HY, well, that directly gives us permission to set up a simple algebraic equation on the right. Because the geometry literally dictates they are equal, we can just write it out. 2x plus 1 equals x plus 5. Basically, geometry gives us the permission, and algebra is going to give us the answer. So let's crack the code. By solving for x in our equation, subtract x from both sides, subtract 1 from both sides, we find that x simply equals 4. But remember, x isn't our final answer here, it's just the key. We take that 4 and plug it right back into our original expression for AH, which was 2 times x plus 1. So 2 times 4 is 8, plus 1 is 9. Segment AH is 9 centimeters. And since we already know all three segments on that transversal are identical, the entire line AC is just 3 times that 9-centimeter segment. That lands us at a total length of 27 centimeters.
All right, on to Section 3, rays and triangle midpoints.
Okay, so the really crucial point here is that this whole logic of parallel lines and transversals, it doesn't just exist in a vacuum. It actually works perfectly as a tool inside triangles, which is super cool. Theorem 3-2 brings this to life. It tells us that a ray drawn from the exact midpoint of one side of a triangle, if it's perfectly parallel to a second side, will automatically bisect the third side, right down the middle. So checking out this visual, if D is the midpoint of the left side and line DE is parallel to the bottom base BC, then point E has literally no choice. It absolutely must be the midpoint of the right side.
Let's see how this plays out in example 3. Here we're looking at a right-angled triangle, and our goal is to find the length of segment CE up on the top right. We're given a massive clue here. D is a midpoint on the bottom, and the line DE is parallel to the vertical side AC. Based on the theorem we literally just covered, this guarantees that E is the midpoint of the hypotenuse CB.
which means segment CE has to equal segment EB.
Walking through this proof, first we establish that E is indeed the midpoint. Next, because DE is parallel to AC and angle A is 90 degrees, well, angle EDB must also be 90 degrees because of corresponding angles. This essentially creates a mini right triangle on the right side, triangle EDB. Now we get to pull out a classic tool from the toolkit, the Pythagorean theorem. We've got sides of 5 and 12. 5 squared is 25, 12 squared is 144. Add those bad boys up and you get 169. Take the square root of 169, and that gives us our hypotenuse EB, which is 13 centimeters. And since E is our midpoint, if EB is 13, segment CE must also be exactly 13 centimeters. Just a really beautiful logical progression.
Let's keep the momentum going. Section 4, the triangle mid-segment theorem. So as the source defines it, a mid-segment is beautifully simple. It's literally just the line segment drawn directly between the midpoints of any two sides of a triangle. That's it. And since triangles have 3 sides, every triangle has exactly 3 mid-segments, which actually creates this smaller, hidden triangle floating perfectly right in the center. And that brings us to Theorem 3.3, the mid-segment theorem. This gives us 2 massive pieces of information to work with. First, any mid-segment is perfectly parallel to the third side of the triangle, the side it doesn't touch. Second, and this is the really important part for our calculations, its length is always exactly half of that third side. Always. So if the base of a triangle is 20, the mid-segment floating right above it is going to be 10. Every single time.
All right, here we go. Section 5, solving complex triangle puzzles.
So let's focus on example 4 right here. Think of this as the final boss level puzzle. We are given this inner triangle made entirely of mid-segments, and we know their lengths. XZ is 6, XY is 5, and YZ is 3 centimeters. Our task? We have to find the total perimeter of the giant outer triangle ABC. Now, we only have these tiny inner measurements, but thanks to the theorems we just unpacked, that is literally all we need. Using our Theorem 3.3 tool, we know every outer side is simply twice the length of its parallel inner mid-segment. So we can rapidly decode the whole shape. Mid-segment XZ is 6, so its parallel outer wall, the base BC, must be twice that, which is 12 centimeters. Mid-segment XY is 5, making the outer right wall AC 10 centimeters. And finally, mid-segment YZ is 3, which makes the outer left wall AB 6 centimeters. Just like that, we've expanded the inner truths to find the outer boundaries. And to find the perimeter, we just walk the outside. Adding our newly discovered outer walls of 12, 10, and 6 together yields a highly satisfying final perimeter of 28 centimeters. I mean, how cool is that? We unlocked the entire outer structure just by looking at its inner skeleton.
We've gone from basic parallel lines to unpacking multi-layered triangle perimeters using algebra, midpoints, and proportion, which leaves us with a pretty fascinating thought to take away today. If finding the hidden midsegments allows us to so easily map out the invisible boundaries of a triangle, what other complex, real-world structures can we decode now that we know how to find the hidden halves within them? Keep an eye out for the geometry around you. You now have the tools to measure it. Thanks for joining me on this explainer.